The topic for discussion in this video is escape energy and escape velocity of an object placed on the surface of a in this case we'll take Earth, right? So let us say there is an object placed on the surface of the Earth. This is Earth, right? And we're going to get an expression for the escape velocity and escape energy of the Earth. Let us first try to understand what do we mean by escape velocity and escape energy. Say an object is lying on the surface of the Earth. Now, when I project this object up into the atmosphere with initial velocity v, the object will go up into the air and then fall back, right? It will adopt a parabolic path and fall back to the surface of the Earth. As I keep on increasing the initial velocity with which I project, the object will go higher and higher, right? For the next case, maybe it will go to higher, it will reach over here and then come back to the surface of the Earth. Okay? Let us say this is the gravitational field of the Earth. Okay? If I increase the velocity further, it will go maybe higher and again come back to the surface of the Earth. But at some initial velocity, sufficiently large initial velocity, the object goes outside the gravitational field of the Earth. That means it reaches over here. It just goes outside the gravitational field of the Earth, and then when that happens, it does not come back to the surface of the Earth. Okay? This initial velocity, when that happens, when the object leaves the surface, leaves the gravitational field of the Earth, is known as escape velocity. So escape velocity, and it is denoted by the symbol v small e, v subscript e. So I have given it sufficiently large velocity. The object has left or has gone out of the gravitational field of the Earth, and when that happens, we say the object has reached infinity, and or in other words, we say the object has escaped from this gravitational field of the Earth, and therefore the term escape velocity. Escape velocity means it has escaped from the gravitational field of the Earth. Okay. The next question, and the next obvious question that we will have, is how do we get an expression for that? The question that we ask now is that how much energy do I need to give this object so that it is able to escape? Right? Now we know that when an object is lying on the surface of the Earth, right, its potential energy over here, potential energy U is minus g me m upon re, and potential energy U here is 0. Potential energy, if I take the potential energy of the object at infinity or outside the gravitational field of the Earth, please note that infinity means outside the gravitational field. So if I take the potential energy over here as 0, then the potential energy on the surface of the Earth is minus g me m upon re. What does this mean? This means that if I give this object energy equal to g me m upon re, it will reach infinity, or it will escape from the gravitational field of the Earth. If you recollect the definition of U is equal to minus g me m upon re, the definition was work done to move an object of mass m from the surface of Earth to infinity. Right? Okay, so the amount of work done to move an object from surface of the Earth to infinity is minus g me upon re. That means if I give this object energy which is equal to g me m upon re, g me m upon re, it will reach infinity. That means it will escape from the gravitational field of the Earth. Right? So that means if this particular amount of energy is given in the form of kinetic energy, it will escape, right? So g me m upon r k, and this will give me the equation g me m upon re is equal to half m v e square, right? Where v e stands for the escape velocity. So, and if I further solve this, I'll get v e square is equal to 2 g m e upon re, and therefore I get v e is equal to square root of 2 g me upon re. Equation 1. So I have got an expression for escape velocity to 2 g me upon re. Interesting thing over here is that escape velocity does not depend upon the mass of this particular object, right? It does not depend upon the mass. It only depends upon the mass and radius of the base body from which it has to escape, right? So if there's some other body over here instead of Earth, if there's some other planet, then the escape velocity for that planet would depend upon the mass and radius of this planet. It has got nothing to do with mass of the object. Okay. A couple of things more about escape velocity. We know that GRE square is equal to GME, right? So if I put this equation in this particular equation of escape velocity, I'll get VE is equal to square root of 2 GRE square upon RE. GME is GRE square, so instead of this GME I have put GRE square, and therefore that will give me square root of 2 GRE. Yeah. Now I put these values, so I'll get VE is equal to square root of 2 into 9.8 into 6.37 into 10 raised to 6 meters. This is the radius of the Earth, and this will give me 11.2. If I solve it, I'll get 11.2 kilometers per second. So escape velocity is 11.2 kilometers per second. This escape velocity is for Earth, right? And it will be same for all objects because it depends upon the mass and radius of the Earth, right? Whatever may be the mass of the object, the escape velocity will be 11.2 kilometers per second. Okay, last point in this video is we'll do a comparison with orbital velocity. In a previous video, we obtained the expression for orbital velocity. VO is equal to square root of GRE, and escape velocity is square root of 2 GRE. Therefore I get VE upon V0 is equal to square root of 2 GRE upon GRE, and therefore I get this equation VE is equal to square root of 2 into V0. Let us call this equation 2. Right? So I have got a relationship between escape velocity and orbital velocity. And what does this mean? It means if there is let us come back over here. Let us say there is a satellite which is moving in this particular orbit around the Earth, and let us say this is the satellite and its orbital velocity is V0. Now if I increase this velocity V0 by square root 2 times, right? If I increase it to square root 2 V0, then it will escape from the surface of the Earth. That means it will leave the gravitational field of the Earth and escape. Okay, so we have got an expression for escape velocity, and we have also looked at the relationship between escape velocity and orbital velocity. In the next video, we're going to look at the energy possessed by a satellite, right, moving around or revolving around the surface of the Earth. Thank you.